and tell us why you picked it. And there's various ways to defend your assumptions and to incorrectly defend your assumptions. That's why we want to be familiar with things like the central limit theorem and the assumptions of the t-test, and when it's robust to like the assumptions of different standard deviations, or when it's robust and when it's not robust. We want to have a good grasp of when that is. Anyhow, so this thing I'm about to show you will help. So, but just keep in mind, there's no right test. There's some wrong answers that we can make and some wrong analyses and some wrong reasons why we would make them. But a lot of times you can pick multiple tests just as long as you're picking them for the right reasons and defending the assumptions correctly. So I want to go out here and share this screen. And if you want to go to Canvas real quick, you can go in there, and it's this hypothesis flowchart Burkhardt. The first cohort, I think it was the first cohort that ever came through about 2.5 years ago. It was 2 years ago. And this guy, Michael Burkhardt, came in. He was a whiz at being at computer graphics and displays and illustrations. He was a whiz at a lot of other things too, but he was very, very good at that. And I was all proud because I had this nice flowchart that I created in Word with like the flowchart little tree diagram stuff, which I thought looked pretty good. Anyway, he was like, "Oh, that is awesome. Yeah, good job, good job, good job." And then he produced this. So he was just kind of, I don't know what he was doing. He was trying to make me feel good because he came up with this, and this isn't perfect. But I mean, there's really no problem with it, but it doesn't cover. It's hard to cover every possible avenue that you could take, but it does a pretty good job. There's only one or two, I think, that it really kind of misses there. So this is good. Let me try to zoom in somehow. There we go. So notice that there is a whole bottom side of this, and again, this is on Canvas if you want to bring it up. It's just a PDF. This is what we're going to get into. So we're not going to worry about this stuff on the bottom. You've seen a little bit about Kruskal-Wallis. I'm going to table all the Kruskal-Wallis stuff until Chapter 5. So just let me sit on that for a week, because Kruskal-Wallis deals with multiple groups, and we're still just want to be focusing on 2 groups. And that's just kind of the way I'll approach it here. But this, we've got more than enough to talk about with just 2 groups. So basically, you can follow along on the screen here, or you can follow along with yours, or both. But I thought I did a great job. So we've got either one sample, or we have matched pairs. In this case, these are both one sample tests. These are, of course, if we have 2 groups. But as you saw in the videos, we're going to subtract those when this is the first time that we're looking at dependent data. So if we have matched pairs, or we have some twins, and we took put one in control and one in treatment, or we gave one a drug and one a control, or we've got 2 people that are very similar. We're going to go over that again tonight with a quick example. But remember, we subtract those, and we just get one set of differences, and then we do a t-test on that one sample of differences. So if we have 2 groups and we subtract them, then we end up with one group of differences, and we can do a one sample t-test on that. Or we've got this one sample. Whenever we have one sample, we're not comparing 2. We're just comparing one mean to some hypothesized value. These are the assumptions you have to make. Is it evidence against normality? If there is no evidence against normality, then take off and go straight to the parametric one sample t-test. Right? There is no equal standard deviation assumption. If there is evidence against normality, no problem if you have sufficient sample size. If you have sufficient sample size, that's when the CLT kicks in. Go to the one sample parametric test. If you do not have sufficient sample size, then head off to the, if you do not have sufficient sample size, then we're going to go to a non-parametric test. And in that case, you can use something like a sign test or Wilcoxon signed rank test. These are typically, I had a lot of questions of this in the quiz too. The sign test and the Wilcoxon signed rank test are one sample or paired sample test. They could be one sample or a matched sample test. So you'll never be competing between the sign test and the rank sum test, or the signed rank test and the rank sum test. The rank sum test is a test of 2 groups, 2 independent groups, whereas the sign test is for matched pairs or simply one sample. we'll go over some examples of those today too. So anyhow, I just thought this was very nice. Like we have to think about, what is our research structure, what's our sample, what's our hypothesis, our question of interest. Then we have these normal distribution assumptions, we have sample size assumptions, we have variance assumptions, of course not for one sample test. There's only one sample, there's nothing to compare to. We could make a data transformation like a log transformation. And notice that this is him saying with log transformation, even if we don't have sufficient sample size, if we do have sufficient sample size but we don't have normality, we may do a log transformation. So I'll just kind of let you kind of go through this. We can go through it more next week if you want, if you have any questions, because I think it's so well written. But these are the decisions that I think you're trying to memorize in your head right now, which when you do this enough, you'll just have them in your head. But this is kind of one mapping of the decisions that you're making as you're going through trying to figure out these tests. Does anybody have any questions just by looking at this real quick? Again, this is the first time you've seen it, so I'll let you kind of go through it. But it's, I think it's a really good mapping. I call that the Burkhardt chart. Cool. All right. So yeah, all this down here is for 2 sampled, and then next week we're going to get into more than 2 samples, which is really interesting. We really want to spend a lot of time this week kind of reviewing, I know you don't have a lot of extra time, but it's going to help. The more that you can really kind of solidify what's going on in these last 3 chapters in this chapter 4, it's going to help you out with what we're about to get into. So we're just going to add another code. Instead of just 2 groups, we're going to compare 3 or more groups. But let's just stick with non-parametric today, where we're still looking at 2 groups. So that being said, I'll just jump right into it. Here is where we are. We're at alternatives to the T-tools, and I put this PowerPoint slide out on the internet. And please fire in with any questions, or hope everybody's doing good out there. I'll take a little break along the way, and I don't know, we'll kind of stretch out on our hike up the statistical mountain, but let's get cracking. So let's go for it. So let's start with an example. So basically, remember we have the t-test, and when we have the assumptions met, when we have normality equal, this is 2 groups here, so we've got a new method and a traditional method. When the assumptions are met, there is no more powerful parametric test than the 2-sample t-test. It is the most powerful test, and you can prove it's the most powerful test in the universe. It's called the uniformly most powerful test, the UMP test, uniformly most powerful of the parametric test when the assumptions are met. Now, that being said, like in a small sample such as this, you don't really ever know if your assumptions are met, and even if they are met, you have a small sample, you may not be getting a good estimate of the mean of the standard deviation. We could run a permutation test here, and I got a question of which test should we run, the non-parametric test, a permutation test, or should we run a t-test? And again, a lot of that's philosophy. Like I said, there's a guy down the way that will only run non-parametric tests, never runs a t-test. Then we've got more parametric people in the department that love the t-test and see no reason not to run a t-test. The caveat to all that is if the assumptions are met and your sample size is big enough, they should give you about the same. If you're testing for the difference in means, they should give you about the same answer anyhow, the same p-value. Now, caveat to that is, remember, so far we've just been looking at differences of means. There are lots we could look at: differences of medians, differences or ratios of variances or standard deviations. There's all sorts of statistics out there that we might want to compare. And we'll get some regression goodness of fit statistics. We may want to compare a bunch of different ones that we don't know the distribution of, a bunch of different parameters that we do not know the distributions of. And if that's the case, we can't run a parametric test, and you're left with the permutation test. So the permutation test is very nice, and we actually, and anytime we have so in this case though, we could run a permutation test on this, or we can run what's called the rank sum test. So let's just go through the rank sum test, and as you know from the videos already, there's even an exact version of the rank sum test. So we'll get there. Very simple idea for this rank sum test. It must be performed on, I'm going to rank these things. That's why it's called the rank sum test. I'm going to rank them. It must be performed on data that can be ranked, and that's called ordinal data, ordinal for order. So they don't, in this case, these are scores where maybe 23 to 24 is the same distance, same meaning from 36 to 37. But you can imagine, again, in a Likert scale, you can run rank sum tests on Likert scales, which we'll see here in a second, where the scores are 1, 2, 3, 4, 5. 1 is very dissatisfied, all the way up to 5, very satisfied. And the differences between 1 and 2 may not be the same meaning as between 3 and 4, or between very, very satisfied and super satisfied. But the Likert scale, that 1 to 5, where you have very unsatisfied to super satisfied, that's still ordinal. So rank sum works well with all of these. But let's check this out. We have this new method and a traditional method. There's only 7 observations, 4 in one, 3 in the other. We go to look at the assumptions. We'd love to run a t-test on these, and many people will, and they'll just run it blindly. But with this data, we don't have a lot of information at all, and even the data we have, it's not super inconsistent with a normal distribution, but just the fact that we have such little, since we have such little data, and there does appear to be a difference in standard deviation, even though it's a very small sample size, we might just want to be conservative and go to an alternative to the t-tools, because we're not sure what distribution we're pulling from, because we don't have a good view, we don't have a big sample from either one of those distributions. So okay, so we remember which situation does it appear that we're in. Make a long story short, we had 3 in one and 4 in the other one, so we're at different sample sizes and different standard deviations. So we might be in a situation like this, where we would be in severe jeopardy of having a biased test, meaning that our p-values aren't quite accurate, and we would be making a bigger type 1 error or a smaller type 1 error, certainly not the 0.05 type 1 error that we're trying to get, that we're trying to maintain. So okay, so we have a problem here. We have different sample sizes, we have evidence of different standard deviations. Maybe the t-test isn't much of a good, the t-test may have low power in this situation. So what can we do? We can run this rank sum test. So we have a non-parametric distribution-free test. It doesn't depend on normality or these equal standard deviations. It does still depend on independence. The trade-off is that the non-parametric method performs somewhat worse than parametric methods if the assumptions are approximately correct. That just means that the t-test is the most powerful test. These may not perform as well if we happen to have the assumptions, but they're very close. And I'll show you a simulation study a little bit later where they're very, very close, and sometimes the rank sum beats the parametric test. So we have lots of choices here. Don't get pigeonholed into thinking there's one correct one. The first one we'll look at is the rank sum test. So again, it's resistant to outliers because all it's going to do is put a rank on the outliers. You can imagine if we had the data 23, 42, 23, I'll put them in order, 23, 42, 18, I'm sorry, it's not in order, 23, 42, 50, 60, and a million. Well, the million's an outlier, but when I rank them, it's just going to be ranked 1, 2, 3, 4, 5, and the million's going to get the 5th. If it was 10 million, it would still get the 5th. So it reels in those outliers by assigning ranks to them. So it makes it a very, very nice test. Of course, that outlier would totally, our t-test is not resistant to outliers. It is very sensitive to outliers. Whereas the rank sum test, yes.
So sorry to interrupt. This is Diamond with the technical support team. You have a student trying to get into your class. Her name is Yume.
Okay.
If you click to the top right, you should see a waiting class. Thank you.
Okay. Cool. Do you need, is this Maxine?
Yeah, if you click to the top right, I can, perfect. She just got let in. Thank you so much, Professor.
Yeah. Cool. Thank you. All right. So, great. Where were we?
Outliers, resistance, t-test is not resistance to outliers where this is.
Thank you. Man, on top of it. I like it. Awesome. So that's right. So the rank sum test is resistant to these outliers. So that's another advantage of this rank sum test. So, and it works well with, works well with ordinal data. It requires ordinal data. interval data is data that's just continuous, but ordinal data is like this Likert scale, whereas the t-test really isn't built for ordinal data. It's built for what's called interval or ratio level data, which is just the number system as we know it. Works well with censored values. I have an example of that too. If you read the book, it'll be the same example. If we have to cut people off and we don't actually get a score, then the rank sum test will work well for that too. Hello, do we have a question?
Maybe
I'm
to
not
go on mute.
sure if that was meant for me. Let me go back to the room. Okay, sorry, did we have a question? Good to see everybody again. Oh, we're good? Okay. All right, well, let's keep rocking. Cool. So far, we're just at rank sum test. So let's do a quick example, and I'll kind of get through my slides here, but I might skip around a few. We'll have more slides here than we can get through. They're just meant for reference. So so here's the example. This is that Likert scale I was talking about. We can use the t-test for this, but it's going to lose power because the differences between poor and fair may not be the difference between good and excellent, right? It might be anyway. You get the idea. That's not the same idea as one shoe and two shoes. The difference in that is a shoe. 4 and 5 shoes. The difference is one shoe. But the difference between, again, somebody's opinion of good and excellent may be different than the difference they feel between poor and fair. But we can use rank sum test for that. So the hypothesis test. So what we want to really get our mind around here, though, is that we're not testing the mean anymore. And for all intents and purposes, we're testing the median because we're dealing with ranks. In the center of the ranks, we're still testing the middle. And the center of ranks of ranked data is the median, right? If I rank a whole bunch of data 1 to 100, and I look at the median rank's about 50, so that's the 50th percentile, and that's the median. However, I can build certain distributions where that's not quite the case with the definition of the median. So I don't want to spend too much time on this, so I'll just draw one picture. If you can see this. So the picture that I want to draw here, and I'll go ahead and make this big, is what's the idea of stochastically greater. So we're going to really test two distributions. It's going to be HL F1 greater, or F1 equal to F2 versus HA, and this isn't the F statistic. This means, when I write it like this means a distribution. So like a normal distribution or some other distribution. So F2, let's say, greater than F1. So what does that mean? All that means is that if F2 is greater than F1, I guess under the null hypothesis, we have something like this. Let's just draw some right skew distribution. So that would be like HO, where for any value, the probability of being greater than that value is the same, no matter if I'm in F1 or if I'm in F2. Right? Oh, and what's the probability being above this? Well, it's that probability, which is the same. So I'd say that the distribution of the probability, that's what a distribution is. It distributes probability values to different values of the on the x-axis. So for this one, it's assigned this probability, it's assigned the same. However, for this one here, it might look something like this, where the probability of F1 of being at this value in F1 so something like that. Oops. So for any value, if this is the case, for any value, for any fixed value, F2 has a higher probability of being greater than that value. So the F2 is greater than F1 in this case. And that's what we're testing here. We're not testing the mean. Turns out that if the shapes are the same, then that'll be true too, that the mean will be greater. But for now, in a strict sense, just in case you ever runs up against, we're going to say in our class that it's really a measure of the median, because that makes sense, because we're going to measure the center of the ranks, and that's what the interpretation of the center ranks is. But in a strict sense, it is the distribution. It's a test of distributions. that's just a technical note. But again, if you just write median instead, it's not a test of the mean. For most, if you write this, or if you write a test of median of group 1 versus median of group 2, that'll be fine. And I'll show you examples of that. So, but here is the distribution of the new method scores is the same as the distribution of the traditional versus the distribution of the new scores is different than the distribution of the traditional scores, or greater than, or less than. So that is the difference, the main difference right now between the t-test and this rank sum test. We can compute the rank sum test with the following steps. That's what we're going to do. We're going to list all the observations, and we're going to assign a rank from 1 to n. If there are any ties, we'll give it the average of the ranks that it's tied in, and identify each observation with its group. You've seen videos on this already, so I'm going to skip. I'll do this in office hours. I usually do an example, but it burns up time. So I think you've seen an example of this. I think it's a really good exercise, but I'll just kind of refer to the video for that. And if you want to see one in office hours, that'll be a great time for it. The test statistic T is the sum of the ranks in one group, in one of the groups. We can find a p-value in one of two ways. We can use the normal approximation, or we can do the re-randomization. The re-randomization is the idea you're very familiar with, the permutation test. If you can remember, we did a permutation test before on the difference of means. We scrambled the labels, look at the difference of means, recorded it. Scrambled the labels, look at the difference of means. This time, we're not looking at the difference of means. It's a different statistics. We're going to shuffle the labels still, and then we're going to rank them. We're going to shuffle the labels, order them, rank them, and then look at the sum of the sum of the ranks, and that's our test statistic. And then we're going to do that many times. This is the bonus on your homework this week, so it's just a bonus. But again, we're going to shuffle the labels, reorder them, grab the sum of the ranks, and then do that many times. If we do that, we will get a distribution, right? This would be something you'd get. You'd get a distribution of 1,000 different scramblings, which means when we order them all, rank them, and take the sum of the ranks of one of the groups, and this is what we would have, and then we would compare the sum of the ranks that we actually observed and compare that on here and count how many were more, or both sides, it was two sides, and that would give us our p-value. However, if our sample size is big enough, then we know that the distribution of the sum of the ranks is normal, is a normal distribution, which is great, which means we can approximate it with a normal distribution. So it's really important to me that you understand how this distribution is being built. We're just going to scramble the labels, rank them, rank the observations with the labels by it, pick one of the labels, pick, say, new method. There's new method and old method. So you're going to scramble the new method, old method labels, then order the values, then rank them, count the ranks of one of the groups, grab that test statistic, do it again and again and again. And most of the time, the sum will be right around some value, some mean value. And that mean value will be right about at nj, where this n here is just the number of elements in that group. So for ours, new method had 4 and old method had 3. So you would pick new method, and this would be 4 times the average of the ranks. 4 times the average of the ranks. And then, so that's the mean, that's the estimate of the mean of this normal distribution. And then the estimate of the standard deviation is simply the standard deviation of all the ranks times the square root of, that's the sample size of N1, or that's the first sample size, so that'd be 4 times 3 in our current example. Sample size of the first group, sample size of the second group, divided by the sum of the sample sizes. And so that's the standard deviation. Once we have the standard deviation, we can build a z-statistic. A z-statistic is just an estimate minus the expected value, or minus the value that we think it's going to be, in this case the mean that we're going to figure out right here, divided by the standard deviation. And we can get a z. And we know that z is bigger than 3 and smaller than -3 or extreme. And we can build z-scores from that. Okay, so the sample, the rank, sampling distribution of the rank sum statistic is normally distributed. And so if we were to do a permutation test, on not the difference of means, but on this rank sum statistic, it would have a normal distribution. So I'm tempted, what time we got here? I'm tempted to really do that real quick. But we'll just keep going through here. Unless anybody's got any questions, then obviously just fire it in.
I got it.
Yes, please.
Question. I thought, and maybe I thought wrongly, that the central limit theorem only applied to averages or difference in averages, and that's why you would end up with a sampling distribution that was normal. What is it about? What characteristics is that allows this this sampling distribution on medians to also approximate a normal distribution?
Great question. And that's because you're dealing with the ranks, and the ranks are symmetric. The rank, right? What makes the distribution of these continuous variables not normal is the fact that they can have these extreme values, right? We can have 1 million, and that really pulls it right skewed, or we can have -1 million, pulls it to be left skewed, or we can have these bimodal distributions. But in any sample, unless, the caveat here is unless we have a lot of ties. If we don't have any ties, then when we scramble these labels under the null hypothesis, the ranks are balanced, right? We're not going to have rank 1, 2, 3, 4, 100, right? It's going to be 1, 2, 3, 4, 5. And when that's the case, since they're balanced, if there's no ties, then they'll just the fact that it's a balanced set of possibilities will generate a normal distribution. The caveat
balanced?
Is ties, though. You could get a bimodal distribution if you have ties. Go ahead.
Is it the case that it's because it's assumed, or maybe it's assumed that that they're balanced in terms of if I take distribution 1 and I take distribution 2 and I'm comparing them and I'm assuming that the medians are the same, which mean they would be balanced. That's what allows me to group them together and then start sampling. In other words, under the null hypothesis. What is the assumption that's allowing me to put these two distributions together and treat them as one and then start sampling from them as if they were one and the same?
Great question. I don't know if you can see the board. Can you see the board?
Yes.
So you just said it exactly. What assumption is it that allows me to put these two distributions and treat them as if they're the same? Because the null hypothesis is that they're the same. The null hypothesis is that those two distributions are exactly the same. In a distribution, it assigns the probability of having a rank sum statistic greater than some number is the same for both. It's the same for group 1, or I'm sorry, the probability of having, in this case, a score. Maybe I will do this example on the board. But having a score greater than 49. The probability of having a score greater than 49 is the same for the new people, the new method, as it is for the old method. So if you see a 49, then the probability is, say, 27% in both distributions. So it doesn't matter if I assign new method or old method to it. I can just scramble under what you said exactly, the null hypothesis. Does that make sense?
Thank you. Yes, it does.
Cool.
Thank you very much.
Awesome. Yeah, great. But a good point brought up there, though, is that the rank sum statistic loses power and has a little more problems because it's not exactly normal when you have a lot of ties. Because when you have a lot of ties, then you can get a couple of 8.5s. If there's no ties, you'll only have 1 8. If there are a lot of, if there's a 10-way tie, you'll have 10 8.5s, and then you'll have this bimodal distribution.
I have a question.
Yes.
Okay, so here we have 7 total 2 groups and 7 samples. If you rank them from 1 to 7, what do you mean by doing it again and again? I mean, are we running the permutation on it, and so are we ranking them again and again? Like, what does it mean?
Great question. So, and it really. So far in my teaching career, this is the concept that is really once we see this of 10-way tie, you'll have 10 8.5s, and then you'll have this bimodal distribution.
Because I have a question.
Yes.
Okay, so here we have total 2 groups and 7 samples. If you rank them from 1 to 7, what do you mean by doing it again and again? I mean, are we running the permutation on it? And so are we ranking them again and again? Like, what does it mean?
Great question. So, and it really, so far in my teaching career, this is the concept that is really once we see this concept, it really has everything come together. And it's not something that you can just get right off the bat most of the time. It's something we have to keep working at, and this is another case of that. So, so the answer to your question is that when I'm saying about doing it again and again, when you think about the sampling distribution, that normal distribution of this rank sum statistic is estimating the permutation distribution, the assumed permutation distribution. So when you say, should I do the normal approximation or should I do the permutation test, in a lot of senses, you're doing the same thing. It's just how are you going to generate that p-value? Are you going to do it manually, where you actually do scramble them and build the distribution yourself? Or are you going to assume that if you would have done that, you're going to get this shape anyway, so let's just go straight to the shape and get the p-value? So in a lot of senses, they're not mutually exclusive. The thing is, you might say, well, with computer powers, let's go ahead and generate the permutation test every time. The problem is if you have small sample sizes and you build a permutation test, you can't get certain p-values, right? If I only have a sample size of 7 here, then my permutation test ends up looking like this, right? Well, maybe even not, that's pretty normal, but maybe the whole number of permutations possible is like 17. And so you say, hey, I'm right here. If I have small enough sample size, I'm right here. The whole thing, I could only get 17 unique permutations. Of that, 3 of them are more extreme, so my p-value is 3 over 17. Right, and whatever 3 over 17 is. But, well, let's just say this is 20. So that p-value from here over would be 3 over 20, which is what? 0.15. Notice that if it's 20, I can only get p-values. This is kind of the key. If I have very small sample size, the number of unique permutations will be small. If it's, as an example, 20, my p-values can only be 1 over 20, 0.05, 2 over 20, 0.1, 0 over 20, 0. So it can only be 0.5, 0.15, I'm sorry, 0.1, 0.15, 0.2, 0.25, 0.3. I can either have, the only way I'm going to reject is if there's none. At the alpha 0.05 level, I can have 0 over 20. That's 0. As soon as I even have 1 over 20, I'm tied with alpha, and I'm going to fail to reject. So a lot of times they might say, well, okay, I can't even get really, unless I don't have any of them that fell above the one that I had, then the one that I observed, then I'm just going to assume that I already know this is a normal distribution. And if I would have sampled many, 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 many more, I know that I'd have a normal distribution, and I can actually get any p-value because this is a continuous surface rather than this histogram. So that's one response as to why you would run the normal approximation, so that you can actually have the ability to reject when there's the only case that you could reject in the permutation test is if all of them are less than the one you observed. But let me go ahead and let me just do this real quick because I think it's going to help us. the data that we had was a new method. There's a new method and a traditional method. I'll just say traditional. New method, traditional method. This was 37, 49, 55, 77. The traditional method was 23, 31, and 46. Awesome. So I'm going to assume everybody can see the board. Please let me know if you can't. But here is the big idea, is I want to be able to tell. Notice just intuitively that of all the numbers here, there's only 7, but we're just going to get as much evidence as we can. 23 is the smallest number. 31 is the next smallest number. 46 looks like it's the 4th smallest number, right? Because 37 is actually smaller than 46. But of the 4 smallest numbers of these 7, 3 of them are in the traditional method. That might say, well, that's a little bit of evidence that the new method, and you can look at the new method, of the 7, of the 4 highest values, the new method has 3 of them. So most of the high values are over here, most of the low values are over here, but there was some evidence against it because this one was 46 and somebody over here got a 37. So how do we do that? How do we quantify that? Because we said, well, it kind of looks like there's more big ones over here than over here, but I need something to help me make that decision. I do the rank sum test. What I do first is I notice their order, and then I'm going to put them in order. So I'm going to say 23, 31, 37, 46, 49, 55, 77. And then I'm going to say, well, let's put our labels by there. That was traditional, traditional. That was new. That was traditional. That was new, new, new. Now it's starting to come together. Looks like the news have migrated towards the bottom and the traditionals have migrated towards the top. That kind of tells me that maybe there's some evidence that the new distribution has higher probabilities assigned to higher scores, meaning that the new method worked. Or maybe that's just random. You know, if I just threw them up there, it's not unlikely that maybe, you know, there's only 7 up there. There's only 7 possibilities to be up there. So maybe just at random, they had to go somewhere. Maybe these 3 ends just landed there. Maybe that just happened at random. So under the null hypothesis, we're saying that the distribution of scores, how I assign probabilities to scores, is the same under the null hypothesis for the traditional and the new. And so what I'm going to do, if I was to run a permutation test, which these are not mutually exclusive, you can look at a rank sum test from a permutation perspective or the rank sum test with approximating that distribution with a normal curve. I'm going to first get my rank sum statistic, and then I'm going to show you what happens when it bounces around. So for my rank sum statistic here, I'm going to go with the T's. So I'm going to say, it's unfortunate because sometimes they use T. I'm going to use S for the rank sum statistic. So I'll say S sub T. That's the sum of the ranks for the T's. Okay, sum of the ranks of the T's. Well, I haven't ranked them yet. So this is rank, that's 1, 2, 3, 4, 5, 6, 7. There's no ties. They all get their own ranks. So the sum of the ranks is simply 7. 1 plus 2 plus 4. That's 7. Question, just for understanding, what is the smallest? If we had the most evidence against, if we had the most evidence that the traditional was the lower and that new method was the highest, just somebody can scream it out because I can't see the board when I'm out here like this. But what is the smallest ST could be? If the most evidence was that traditional was the smallest, what's the smallest that ST could be?
Could it be 1 if they were all tied?
Okay, great. It could be 1 if they were all tied. Let me say the smallest with this data.
6?
Exactly. Perfect. That's where maybe I didn't phrase it quite. But it's true. If they were all tied here, it could be 1. But with this data, if these were switched, it would be 1 plus 2 plus 3. Right? That would be if the traditional had the 3 smallest and the N had the 4 biggest. That would be the most evidence towards N being the new method working. That would be the most evidence. And this is the next best thing, ST of 7. So we want to know how unlikely is it that if there really is no difference in these, that I would see something this extreme, that I would just get these t's at random down here and these n's up here at random. And if it's not very unlikely, then I'll fail to reject the null. So that's what we do. We say, okay, one way would be, so let's record that. This one here was ST equals 7. One way would be to go ahead and just scramble the labels. Let's just scramble them. I'm not a true random number generator, but I'm just going to fill them up here. And I fill them up, I get NT, N, T, T, N, N. I just throw those up there. Well, that's an ST of what? Just at random. That's a 2, that's a 6, that's an 11. That was an ST of 11. Okay, let's do another random one. Try your own, you know. N, T, T, N, N, T, N, T, T, N, N, T, N. Okay, let's see what that one at random happened to be. That was a 2, that's a 5, and that's an 11. That's another 11. Huh, that's odd. So let's keep going. It's not really odd, because we'll try another one. Let's just say I just throw them up here. Okay, T, N, 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 T, N, T, T, N, T. So one more time. That's a 1, that's a 6, and that's a 13. That's ST equals 13. Okay, we're getting tired of that, but I've done 1, 2. Well, this one I'm not counting, because this is the one I observed. But I've randomly scattered them 3 times. Now imagine I did that 1,000,000 times, right? Or 10,000 times, maybe not 1,000,000 times. Say I did 1,000 times. Looks like 11 comes up pretty often. And it looks like 13, it would be unlikely that all the t's would end up down here. That wouldn't happen very often. There's only one way that could happen. But if that happened, that would be a sum of 11. The biggest it could be would be 18. The biggest ST could be is 18. The smallest ST could be a 6, and it's going to be somewhere in between. So what I would do is run that. The smallest it can be, if somebody would let me know, can you see that right there? That line?
That's good.
You're good right there? Okay. So the smallest it can be is 6. The biggest it can be is 18. But they're equally likely, the 3 are equally likely to end up down here as they are up here. That comes from that balance part that we're talking about. And they're the numbers are 1, 2, 3, 4, 5, 6, 7. So it's just as likely to be a 6 down here as it is to be an 18. And if I do it 10,000 times, a couple of those 10,000 times, the 3s are going to be in the bottom slot. So that's those. A couple of those 10,000 times, the 3 are going to be in the top spots. But more often than not, they're going to be mixed up like they are in here. So I might get a lot of 11s. So that's 6, 7, 8. We might get something that looks like that. And we would want to know, that certainly looks like a normal distribution, but what we would want to know is, okay, I observed 7. 7 is right here. And that would be my p-value. Right? 7's the second smallest thing it could be. And if we say that doesn't happen very often, then we'll say, oh, okay, well then, if that can't happen very often, then we'll say, oh, all right, then that has a small p-value, and we'll reject the null. Because what we observed would happen very rarely under the assumption that we can just scramble these labels any way we want, under the null hypothesis that there's no difference in distribution. That's the first kind of stopping point. But let me continue then, or just fire away if you have a question. That's how we would do it with a permutation test. This is the exact test. When you're looking at Dr. McGee do it on film, and I got some questions on how to do this in SAS, and I'll have those out here too. But this is the exact version, right? And if this is built from not a very big number of possibilities, then this p-value could again be 0 or only 0.05 or 0.1 or what have you. So what people said was, I know that this is approximating a normal distribution. So instead of writing this program that counts it, let me just estimate what the mean and standard deviation are. And so what do we do? And from semester to semester, I forget what the mean of this thing is, so let's figure it out. The mean of this distribution is estimated to be N1, I'll call that NT, times R bar. Well, NT times R bar, NT is 3, right? There's 3 T's. NT is 3, and R bar is the average of the ranks. R bar is the average of those ranks. So I'm going to do 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 divided by 7, that's 3.5, right? Divided by 7, or it's 4. Well, there you go. So that's, so divided by 7, that's 4. Oh, that makes sense, right? That's the one that's right in the middle. So this mean right here, mu, is estimated to be 3 times 4, which just makes sense, right? That's halfway between 6 and 18. We could have figured it that way too, which explains why when I was doing it random, why I got so many that were 2 out of 3 were 11, and the other one was just on the other side of 12. Which, you know, maybe I am good at making random numbers. So, so anyway, so that's what we're doing there with the permutation test. But now if I just assume this normal distribution, I'm going to assume it has a standard deviation of 12, a mean of 12, and now I have to estimate the standard deviation. And the standard deviation of that guy, so it's 3 times 4 here. So, yeah, so the standard deviation of this guy is estimated to be SR times the square root. I'm kind of not doing good on my board space here. Times the square root of 3 times 4. That's just NP times NN. It's 4 times 3 divided by 3 plus 4. So SR, which we're going to have to get, that's just the sample standard deviation of 1, 2, 3, 4, 5, 6, 7, times the square root of 3 times 4 divided by 7. So if I did that real quick, I encourage you to try that. I got a quick way to do it here. So second quit, second stat, calc, one of our stats, 3. The sample standard deviation is 2.16. So sigma here, I'll just put it down here, sigma is estimated to be, sigma hat, 2.16 times the square root of 12 divided by 7. So times the second square root of 12 divided by 7 gives us 5.23. So the mean is 12, and the standard deviation is estimated to be 5.24. And from that, you can build a z-score. My mean is 12. My estimated standard deviation is 5.24. So my z, so I'll put right here, is equal to what I observed, which was a 7 minus the mean, which is 12, divided by 5.24. 5.24. And lo and behold, that's -5 divided by 5.24. We did something wrong. I got a z-score of -0.954, which doesn't sound quite right. Let's make sure we did that right. I know the 12's right. This guy, 12 divided by 7 is SR. Make sure I got my formula right there. That's right. Well, it is right. That should be about like that. So, well, let's just say it's that. So if that's it, then this right here, this 7 would have a z-score of -0.954, which would actually have a pretty big, that's not a very extreme p-value, or that's not a very extreme z-score. So it would have a pretty big p-value. But so it kind of looks like it has a small p-value here, but at -0.94 it would have a much bigger p-value. Does anybody have any questions over that piece? I'm going to erase this and blow this piece up here real quick, unless anybody has any questions. Hopefully that kind of shows you what's going on with this rank sum test, so that we can use it. That's the idea. That's the strategy of this test. So I'm going to redraw this. This is a 12 down the middle. This is an 18. This is a 6. And so if that's a 6, 7, 8, 9, 10, 11, 12. So this is 12, 13, 14, 15, 16, 17, 18, 11, 10, 9, 8, 7. Not perfect, but that's the idea. I'm going to show you the continuity correction here shortly. So let's get caught up. So there's what we just did. We just did the mean is one of, pick whatever your reference group is. So pick N1, that was NT times R bar, and that's SR times the square root of 3 times 4 divided by 7. Right in there. Then we made our Z-score, and then we can find our T-statistic. So that was our chalk talk. Awesome. Check. So here is when we have here's what we do when we have, SAS do it. So when we have SAS do it, it comes out to be, they got theirs, I did something wrong there. Their Z-score turned out to be negative 1.59. Mine was negative 0.954. I'll find out what I did there in a second. That was bad. But they should be about exact. Oh, I know what